seen with rigid transformations or isometries that if we have a rigid transformation from an image to from a pre-image to an image, then those two objects are congruent. Now, it turns out that with dilations, if the k, if that scale constant is not equal to 1, then the two objects, the pre-image and the image, will not, in fact, be congruent, but they will be similar, which would mean that all the angles are the same and the ratio of corresponding lengths will always be equal. Namely, the ratios are equal. Basically, what it's saying, this for us, for you and I, imagine if you drew something, you put it on a Xerox machine or, make a copy or a copying machine, and you set the scale to 0.5, it'll come out being half as big. Or if you set it for, 2 times, and it'll be twice as big. It's the same figure, but expanded or contracted. So those are similar figures. So we can actually prove that two geometric objects are similar by just merely showing that, in fact, there is a dilation that takes one to the other. So, for example, look at triangle ABC. ABC, that's the green triangle here. And look at triangle DEF. And the question is, are they similar? Well, the answer is they are, especially we can prove that if we can find a dilation map that will take one to the other. And in this case, it's actually not too hard to see what I need to do here. What I need to do here is take this green triangle and expand it, kind of blow it up, if you will. And I got to blow it up so that, in fact, this A point of 2 is going to equal the D point of 5, which means I have to multiply A by 2.5. Now let's see if that works across the board. If I take this point, 2, -2, and multiply it by 2.5, do I get 5? And the answer is yes, because 2 times 2.5 is in fact 5. And finally, if I take this point, -2, 0, and I multiply it by 2.5, what happens? I get to -5, 0. So you can see that, in fact, these two things are similar, and the proof is I can actually give you the map that's a dilation, namely x, y gets mapped to 2.5x, 2.5y. It's a dilation map with dilation scale factor of 2.5, again, center at the origin. These two objects are, in fact, congruent. Not congruent, similar, right? You can see they're not congruent. Why would anyone say that? Let's take a look at another example together and see this idea in action. So here I'm going to give you the coordinates for two quadrilaterals, ABCD and EFGH. And you can see them here. The ABCD is the green thing and the EFGH is here. Are they similar? Well, let's think about it and see. Can I get some kind of rigid transformations together with a dilation to get one to the other? And the answer here actually is no. Now let me tell you how I think about it, and then I'll actually show it to you for real. I look about it and say, if I were to put this on a copy machine, is there something I can set that would blow it up to this? And the answer is no, because check it out. This is actually has length 2 and length 2. This is a square. And this has length 1, 2, 3, 4, 5, 1, 2, 3, 4. This is a 5 by 4, and this is a 2 by 2. There's no way to take one factor, scale factor, and blow it up and make the two at once a 5 and a 4. So I can tell right there it can't happen. If you want to really prove it, here's a really cool way of proving it. You could take the red square and do a translation over 1, 2, 3 units to the right. So that takes xy and sends it to x plus 3y. And then you can take the green and send it to 1, 2, 3, 4 to the right and 1 up. So x plus 4, y plus 1. And if you do that rigid transformation, then, of course, what we know is they would still be congruent to the corresponding things. So this red square is congruent to the original red square, and the green rectangle is congruent to the green rectangle. Now you look at this and say, okay, can I get from here to here with one dilation? And the answer is no. And you can see that now very clearly. To make this vertex blow out to here, this is 2, this is 4, I got to multiply by 2. So that's a 2 times. But if I multiply this by 2, it only get me to here, not all the way to here. So that shows, that proves that these two geometric objects are not similar. Because in fact there's not a way to get from one to the other with dilations and rigid transformations. So kind of cool. You can actually get a lot out of this idea. Let's take a look at one more example, which is to take a look at these two triangles, ABC and DEF. And I want to ask, what can we say about these guys? Are they similar? And the answer is yes. And the way to see that is to realize that we have to put a combination of things in play here. I'm going to do it just like the last question. The first thing I'm going to do is use a rigid transformation to take this ABC so that the C is going to be located at this F point. So what does that involve? It involves me sliding over 1, 2, 3, 4. So I send X to X plus 4. And I'll send the y values to y, 1, 2. So y plus 2. So that's a rigid transformation. And now, once that's in place, what do I do? Well, now I ask, is there a scale factor that I can use for dilation? And the answer is sure, because to get this 2 point to this 4 point, I just have to multiply by 2. But is that also true here? Well, notice this point is at 3. If I multiply 3 by 2, I get 6. So now the dilation xy mapping to 2x, 2y blows this thing up, this little blue triangle, to the red triangle. And that proves that the original green triangle and the original red triangle are similar, because there was a translation and a dilation that took one to the other. Excellent. So now we can tell when two objects are similar, and we can actually prove similarity if we can actually find the appropriate transformations. How cool is that?